3, 2, 1, sequences 2. Alright, so here is our second in our sequence of 3 videos on the exciting world of sequences in analysis. Okay, so last time we established what sequences are, and we talked primarily about their convergence, and we proved some results that were hopefully quite familiar from calculus. Not exhaustive, but, a good sampler platter. I don't know where I'm going with this. Anyway, so today, we're going to talk about property of sequence. So our main goal for today is to prove a very famous theorem about sequences, one you did not see in calculus, that has some serious implications for how the real numbers behave, and why, in addition to the least upper bound property, the real numbers also have another fundamental property to them that distinguishes them from other totally ordered fields, such as the rational numbers. Alright, okay, so I kind of foreshadowed what we're going to primarily talk about, which is subsequences, and before we get there, we have to introduce something that we've mentioned, but we haven't actually given an actual definition, and of course when we get to derivatives, this is going to be something we will investigate. Strategically? What? I spelled it right, and then I spelled it... yeah, sometimes... Oh, and my spell checker doesn't even... It's one of those where the spell checker... millions of dollars of technology is looking back at you going, yeah, I don't know. I got all the words, and I don't know. That one doesn't look like any of them. It's not that far away, too. It's just, a pair of letters, and it's not the... interesting. What's it? I think that's a Bill Burr bit. Like an old, back when he had hair. Anyway. Yeah, good old Billy Rednuts. Alright, let's get going here. Alright, so we're talking strictly increasing and strictly decreasing, and these are what you expect them to be, similar to monotone increasing and monotone decreasing, only now strict is requiring it to be strict, less than rather than less than or equal to. The only difference between the two. Okay, an interesting property of strictly increasing functions is the following. If I have a strictly increasing function from the natural numbers to the natural numbers, then the mapping needs to be expansive, right? And this is a property we've seen a couple of times. In fact, this is a pretty common theme in the theory of monotonic functions, where you kind of look at things like this. So we kind of already seen this showing up, and it's not too surprising. But anyway, so if you have a strictly increasing function from the natural numbers to the natural numbers, then the output always must exceed the input. And if you think about it, that makes quite a bit of sense, because phi of 1 either is 1 or it's bigger. Phi of 2 needs to be strictly bigger than whatever phi of 1 was. So, right, phi of 1 is strictly, phi of 2 is strictly bigger than phi of 1. Phi of 1 is at least 1, which means phi of 2 needs to be at least 2, and so on and so forth. So, as you can see right away, it's pretty easy to inductively argue this, but we're going to go with another approach, which is kind of this, reverse induction idea, where instead of inductively showing this is true, instead what we'll do is, okay, so we'll set up a set, and what I want is the set to be empty, because if it's empty, then this never holds, which means this always has to hold. So, we suppose the set is non-empty, and it's a non-empty subset of natural numbers, so that means it's a non-empty bounded below subset of integers, because every natural number is greater than or equal to 1, so it must have a minimum, and the existence of a minimum is going to be contradictory. So that's why I was saying that this is kind of like a reverse induction argument, where rather than starting from 1 and incrementing ourselves up to getting all the natural numbers, we will set up a set, we'll get a minimum, and then we'll show that we can decrement ourselves down, but we're at the minimum, so decrementing cannot happen. So it's kind of like reverse induction, maybe. Although, side note on reverse induction, I was told once by a student, a former student, they were at a grad class, and they emailed me, and they asked me if I'd ever heard of induction where you start from infinity and go backwards. And I still have no idea whatever that professor was on the pack. That's whatever. Man, I'm on fire with the references right now. It's gonna be a great comment in the student evaluations. He kept talking about shit. I had no idea what the hell he was saying. Anyway. Anyway, okay, so we set up this set. Suppose it's not empty. It's got to have a minimum. Okay. Now, minimums belong to the set, so that means we must have this property. So, hey, my function is strictly increasing, so I've got this. But what does this mean? This means that phi of n needs to be in the set. Phi of n is a natural number that satisfies that condition. So phi of n is an a, but the minimum of a is n. So that means n is less than or equal to phi of n, and once again, our favorite result, phi of n strictly less than phi of n. Contradictory. Once more, I told you, it's probably going to be the most used fact in this course, that any real number is not strictly less than itself. And I'm really not joking, where like a lot of the arguments ultimately boil down to that. So, alright, cool. And it's a slick little... I love this proof, too, because this is another proof, in my opinion, that is very just sort of... Right, this hypothesis gets used exactly once, and in a very key way, because this just unravels the whole thing. So, pretty cool. Alright, and there we go. Now, I want to we're not going to actually do anything with strictly decreasing, but since we were talking strictly increasing, I wanted to, at least mention it. We'll talk a little more about this when we get to derivatives, which will be in 3-4 weeks, something like that. We still got series and continuous functions to talk about, so derivatives are a little bit off the way. Okay, but anyway, so there's a reason I wanted to talk strictly increasing, because a subsequence of a sequence is defined as follows. You give me a sequence, and instead of going 1, 2, 3, 4, so on and so forth, I am now going to put a strictly increasing function. So note, a subsequence is not necessarily just a subset, right? It's not going to be like x3, x4, x2, x1. It's not a rearrangement. It is literally, we're going to go down 1, 2, 3 strictly and only pick certain ones. So some classic ones are, of course, just picking the even numbers or picking the odd numbers, right? That is a strictly increasing process. We also could pick the prime numbers if we really wanted to get sassy. But, yeah, so notationally speaking, we don't usually write it like this. In the same way that sequences are technically functions, but we always write them in a notational, an index notation. Same is true for subsequences. We instead actually write them as follows, where it's understood that n sub k is a strictly increasing function from the naturals to the naturals. Now, this gets really obnoxious because... if I remember right, we're not going to encounter it, but there is situations where you want to do a subsequence of a subsequence, so you have like an n here, and then like an n, and then a sub k. It gets brutal with the notation, which is why sometimes this is a little bit better, because then you just have a composition of two functions you can work with. But anyway, so that's all a subsequence is. It's just, I'm taking the sequence, and I'm just going down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I am just throwing out some of them. Right. Now, it turns out that studying the behavior of subsequences is an incredibly powerful tool. It, at first glance, may not seem like anything too interesting, right? And your initial reaction to this could just be like, yeah, I bet that's something. But it's astonishing what the something is, and what we're going to be able to extract from this pretty basic idea. Right. So the first thing I want to prove, to give us a flavor for how subsequences work, is a pretty important result, which is that if we have a convergent subsequence, if we have a convergent sequence, then every subsequence converges to the limit. And that hopefully makes sense, right? We should immediately sort of see why that would be true, because if our sequence is converging, alright, well, then if I just go down the sequence and strictly increase and pick certain elements, I'm not going to lose the gets close and stay close. If anything, I'm going to expedite the process because I'm going through the natural numbers faster than normal. All right. So, and typically, and actually, as we just proved, we kind of think this is saying that we're going for the natural numbers just as fast as counting a 1 by 2, 3, 4, so on. In fact, we're possibly going even faster. So, not too shocking, but we do need to prove it, and good thing we explicitly prove this, because we're going to be using this fact repeatedly today. Alright, so, typical things, let epsilon be greater than 0, then since we converge, there is an n, so that x of n gets within epsilon of the limit for all n greater than n. Now let k be bigger than n. Since we have a subsequence, that means the n sub k's need to be greater than or equal to k. K is bigger than n, so n sub k is greater than or equal to n. And so this must be less than epsilon, and there we go, our subsequence indeed converges. Because given an epsilon, I can find a capital N, so that for all k, this gets within epsilon. That's it. So, no, this was a pretty standard unravel the definitions proof. The only sort of key step here was knowing that fact about a strictly increasing function. So, which we already took time to prove. But everything else here was just unraveling what does it mean to converge, right? Given an epsilon, there is an n, so that this works. And then just applying the one bit of information we need, using the one fact about what it means to be a subsequence, and finishing the proof. Alright, beautiful. So not too bad. Alright, so whenever you prove a statement that's of the form P implies Q, so convergent sequence, then every subsequence converges, then you want to ask, well, let's say if I know subsequences converge, does that mean the original has to converge? And in general, the answer is no, because a sequence can be divergent but have convergent subsequences. So we've already seen the example of this. The sequence -1 to the n we know is divergent, but if you only pick the even numbers, you have a constant sequence which converges. So it's possible to have convergent subsequences, but be a divergent sequence. And that's going to be kind of our goal now, is to study the existence of convergent subsequences. So if we have a convergent sequence, then every subsequence is convergent. So that's not interesting. So the more interesting thing now is to study sequences with this sort of behavior, where I don't necessarily know the sequence converges, but I do have access to convergent subsequences. Alright. So that's going to be our main goal, and that's going to be the big theorem we're going to go after, which is a theorem guaranteeing the existence of certain convergent subsequences. Alright, and so as I referenced in the previous video, we saw what I consider probably one of the most important proofs you're going to see in the course for a lot of the little tools and logical arguments and sort of the thematic, ideas that were present there. And then in that video, I forewarned that in the next video we're going to see the opposite end of the spectrum. We're going to see a theorem whose proof is just incredibly technical and requires a lot of build-up, and we need to prove it because the conclusion is incredibly useful, and that's what we're after now. So we are going to begin building up a bunch of stuff, and it's going to come to head in a very technical theorem, probably the most difficult theorem we're going to see in the course. Just in terms of all the machinery that's running around. Maybe not the logical arguments. There might be some more difficult ones later on, like conceptually, because conceptually what we're about to work with is not too bad, but there's a lot to keep track of, and the proof of the theorem, which again I don't want to spoil it just yet, is going to be, again, it's not going to be awful. It is going to be significantly involved, and it's going to span like 4 slides, so it's incredibly important. It's so all right. Well, I'm hyping it up. I'm building it up like it's going to be this terrible thing, and then when you get there, you'll be like, oh, this isn't that bad. Hopefully, that's your reaction. But anyway, alright, so our goal is to talk about the presence of convergent subsequences, and it turns out a great way of doing that is to look at what's typically called the nth tail of your sequence. So for given a sequence, we define the sets T sub n to be the collection of x sub n's, so that the index k is bigger than the prescribed n. So T of 1 is just the sequence, T of 2 is a sequence but starting at 2, T of 3 is a sequence starting at 3, so on and so forth. So t a billion is the sequence, but starting at the billionth term. So these are called the nth tails, or something equivalent. Our book doesn't give them a name. I just think it's nice to have a name for these, because we're going to play around with these quite a bit. And naturally, kind of going after these seems like a reasonable thing to do if we're looking for subsequences that are going to behave, because, right, note, this is kind of like going after, like, this is a strictly increasing sequence, right? I skipped one, right? I skipped 1 and 2, so makes sense, right? These are technically generating subsequences, right? They're just, right, we're strictly increasing. Right, so 1 is going to 2, 2 is going to 3, so on and so forth. Okay. Now, the key thing that we're going to do now is turn our attention to bounded sequences. And why would we do that? Well, if we're going for convergent subsequences, it's going to be a lot easier if we were working with a bounded sequence, because in order for a convergent subsequence to exist, that means you need a bounded subsequence, so we may as well just have a bounded sequence to begin with. So it's worth noting that everything I'm about to talk about, there's technically a way to get to all of this stuff without assuming a bounded sequence, but it gets very messy, and I'm not a fan of it, so we're just going to cut our losses and just focus on the bounded sequences. But anyway, so if our sequence is bounded, then every one of these sets are non-empty, and they're bounded above and bounded below. So if the original one is bounded, that means x1, x2, x3 is bounded above by something, which would mean that x2, x3, x4 is bounded above by something. And likewise, if this is bounded below, then this one must be bounded below, so on and so forth. So if I have a bounded sequence to begin with, then each one of these is a non-empty, bounded above, and bounded below, which means I have access to infimums and supremums. So for any bounded sequence, then, the nth tails have infimums and supremums. And we can generate these sequences, and I've never seen a good notation for these other than A sub n and B sub n, which are very generic. But, yeah, I don't know of a better notation. Maybe like an X sub n with like a down arrow and an up arrow or something. I don't know. But anyway, so given a sequence, we can create its nth tails, and if the sequence is bounded, then I can create these sequences of infimums and supremums. Okay, and for the most part, we're going to abandon the T sub n notation that I introduced here. This was just mostly for effect, so you can kind of get a view for it. I'm mostly going to write it just as it actually is. But if you want to use the T's, you can. But alright. So, it turns out that if I have a bounded sequence, I have access to this sequence of infimums and this sequence of supremums. And guess what? This sequence of infimums always converges. Ooh. And this sequence of supremums always converges. So, for any bounded sequence, I'm able to create two convergent sequences. So, okay. Alright, so here it is. Our very nice theorem about the convergence of the infimum of the tails and the supremum of the tails of a bounded sequence. So specifically what we are going to verify is that A sub n and B sub n are related to each other as follows, which hopefully looks very familiar because we saw this in the proof of Cantor's uncountability of the real line. And furthermore, we will, from this fact, point 2 and point 3 are basically for free. So note that point 2 says that my sequence of infimums of my tails is a bounded above monotone increasing sequence. And as we proved in our last video, we know that it must be convergent. We did not prove that the analogous result of bounded below and monotone decreasing is also convergent. But like I said, we're not aiming for exhaustive, we're aiming for illustrative, and the proof of this being convergent is the same thing as the proof of this being convergent, just swap your inequalities. Alright, and yeah, and the spacing is weird here. I don't know. Yeah, I got my align going on, and then I got an enumerate, and LaTeX decided, yeah, you need a big old gap right here. So, sorry about that. Alright, well, let's get into the proof. So, like I said, kind of the tricky part here is just part 1, then part 2 and part 3 come for free. Okay, so in part 1, first we'll establish that a sub n plus 1 is less than or equal to b sub n plus 1. This is pretty easy because x sub n plus 1 needs to be in the set, and that means x sub n plus 1 is less than or equal to the inf and less than or equal to the sup, and so a sub n plus 1 is less than or equal to b sub n plus 1. Not too bad. Okay, so the tricky part is going to be the next argument. So note that anything that's in this set has to be in this one. So if you're in the nth plus 1 tail, you're in the nth tail. And that should make sense because, right, if k is bigger than n plus 1, then k is bigger than n. Now, the tricky part here is going to be the following argument. Pick any element that lives in here. It lives in here. So anything that's a lower bound for this set must be a lower bound for this. And vice versa. Anything that's an upper bound for the set on the right is an upper bound for the set on the left, because everything in the left is in the right. So that means the infimum of this set is a lower bound for this one, and since the infimum of this set must be the greatest lower bound, that means the infimum on the right is less than the infimum on the left. And right, and at first glance that goes maybe a little bit against your intuition, but remember, this set has less elements. I took things away. And if I take things away, my infimum can only ever get bigger. Right? I can't take stuff away and my infimum becomes smaller. And likewise, anything that is a supremum here is a upper bound for this, which means the supremum here is always going to be less than the supremum there. And again, that makes sense. If I've got a collection of things and I start removing stuff, the sup can only go down. I can't take things away and the supremum increases, because what I have is still bounded by the original. I can only get smaller. So these two inequalities must be true. So the infimum on the right is less than or equal to the infimum on the left. So a sub n is less than or equal to n plus 1. And likewise, the supremum on the right is bigger than the supremum on the left, because the supremum here is a upper bound for this set, and the supremum is the least upper bound. Okay, right, so remembering how inf and sup behave, right, this is the greatest lower bound, this is the least upper bound, justifies this, but also I always liked, the way I always kept it straight in my head was, this set, I've taken things away. If I take things away, my infimum can only get bigger, and my supremum can only get smaller. Alright, and so that establishes that a sub n is less than or equal to a sub n plus 1, and b sub n plus 1 is less than or equal to b sub n. So that completes the proof of part 1, and then for point 2, we note that point 1 guarantees that a sub n is always less than or equal to b sub 1, and so... and so nothing. Why is it just like... and so this is bounded above. and so the sequence. Ooh. good thing you told me. and so the sequence is bounded above. And moreover, we get the monotone increasing because we know that a sub n is less than or equal to a sub n plus 1. So a sub 1 is less than a sub 2, which is less than a sub 3, so on and so forth. So we must have a monotone increasing sequence. Cool. And similar for point 3, the b sub n's are bounded below by a sub 1, so we've got a bounded below set, and b sub 1 is bigger than b sub 2, which is bigger than b sub 3, so we have monotone decreasing. Alright, beautiful. So, for any bounded sequence, the previous proposition ensures that I have access to the following limits. Right? The infimums of the tails of the sequence is a convergent sequence, so I have access to the limit. And likewise, the limit of the supremums of the tails also exists. Man, I really want to just glue these together. I don't know about you, but I want those to be a thing. And indeed they are. So this, which is the limit of the infimum of the tails, is called the limit inferior, and we write it as lim inf of the sequence. And likewise, this is the limit of the supremum of the tails of the sequence. We call that the limit superior. Beautiful, right? Nice, clean, straightforward. Limit of a bunch of infimums, that's the limit inferior. A limit of a bunch of supremums, that's the limit superior. So these are known colloquially as lim inf and lim sup. So I have a very fun shirt with a bowl of soup with a bunch of limbs in it, and so it's lim soup. Very exciting. So, for any bounded sequence, you always have access to lim inf and lim sup. These always exist. The limit of the sequence may not exist, but you always have its limit inferior and its limit superior. These are always a thing. So that's good news. So it turns out, as we will see a little later on when we get to a series next week, some very famous limits that you know were actually lim sups. You were lied to in calculus, specifically in the ratio and the root test. It's not the limit, it's the lim sup. Alright, cool. Now, note how they're defined, right? This is a limit of a bunch of infimums, and this is a limit of a bunch of supremums. Pretty cool. However, there is a bit of a counterintuitive thing. These limits exist. Now, remember what we just proved. We proved that the infimum of the tails of a bounded sequence is a bounded above monotone increasing. So its limit exists, but what is its limit? Its limit is a supremum. So this is bounded above a monotone increasing. So its limit, which is the limit inferior, is actually a supremum. And that could be right away. You should be angry. You should be like, "Oh, come on!" Right, but no, you want to call this the lim inf because this is the limit of the infimums, and you want to call this the limit superior because this is the limit of the supremums. But the lim inf is actually a sup, and likewise, the lim sup is actually an inf of something, which is very. It's your first reaction to that should be like, "Oh, that sucks." And it does, and it will trip you up. I remember when I first learned this stuff, and when it dawned on me that I was like, wait, lim inf is actually a sup? I was like, that's fucking stupid. But it's not, right? Because you want it to be the limit of these infimums, so limit, yeah. But, yeah. So, it's technically a sup of a bunch of imps. That's what the lim infimum is, and lim sup is the infimum of a bunch of supremums. So, okay. Anyway, so hey, lim inf and lim sup. Now, note these things converge, but note something about them. Again, remember, kind of our goal here was to investigate convergent subsequences, and I have not constructed a subsequence at all here. Right? These infimums, right, they don't belong to the set. If they were minimums, they would be in the set, but it's very possible that they're just infimums. Right, so for example, if x sub k is 1 over k, then, we know the inf of that is 0, and that's not an element of the set. So, the limit inferior and the limit superior here, these are limits that always exist, but note the way they were created. They were created using just infimums and supremums of sets. I never actually used the subsequence. That's why the next theorem is as powerful and as important as it is, because it turns out, for any bounded sequence, lim sup exists, lim inf exists, and I can always find you a bona fide subsequence of elements that will converge to the lim sup, and a subsequence that will converge to the lim inf. Although I use the same notation here, they are not necessarily the same. More on that in a bit. And so here is the theorem that I bigged up before we got here. This is the Bolzano-Weierstrass theorem. Okay. Now, it's worth noting that this is similar to the Naster-Tarski theorem. What I presented to you is technically a version of it. It's not the most general version of the theorem. And the same is true for Bolzano-Weierstrass here. This is a version of the Bolzano-Weierstrass theorem. The more general one is a bit more broadly stated, but for our purposes, this is good enough. All right. Similar to Nastor-Tursky, Bolzano, Weierstrass, a couple of famous mathematicians, and as I promised in the last video, I was going to reveal the bastard who cooked up epsilons, and it's your boy Weierstrass. So if you want somebody to damn for all of eternity for making you do an epsilon proof, Weierstrass is the one who cooked it up. But Bolzano should get a little blame too, because Bolzano more or less had the same ideas. So Bolzano was in the early 1800s, and Weierstrass was towards the end of the 1800s. Specifically, the epsilon delta argumentation. Cauchy was essentially doing similar things, and Bolzano was basically doing it. Weierstrass is the one who sort of codified it, and that was like 1860 or so, somewhere around there. Good stuff. So Weierstrass is German. Bolzano, if I remember right, is Czech. Although at the time that would have been like Bohemia or whatever. Ask Professor Ledisky. He could probably give you a whole history of some Czech mathematics. All right, but yeah, so Bolzano and Weierstrass, very instrumental individuals in the history of analysis, and note those dates, 1800s, and that was a long ago. And again, the history of math, which has been a facet of human history, like this is recent stuff. All right, cool. Okay, so. Alright, so as promised, this is going to be the first really difficult theorem we're going to have, so let's jump into it. So, alright, so like I said, this is going to take a few slides. It's not awful, it's a lot. So we're going to, let's take it easy. Take it easy, man. I hate the Eagles. Alright. Yeah. Alright. Okay, dude. Let's go. Alright. So, first things first, we're just going to prove 1, and then we'll note that 2 is just a very similar proof. So, the lim sup, remember, is the infimum of the supremums of the tails of our sequence. Okay. And then the lim inf is the supremum of the infimums of the tails of our bounded sequence. Okay. Alright. So, what do we got to do? Okay. So, here's the plan of attack. So first, okay, I'm going to demonstrate that I've got a subsequence converging to the lim sup, so let's let alpha be the lim sup, and as noted, remember, this is the infimum of the supremums of the tails, and like I noted, when talking about the supremums of the tails, we use a generic symbol, b sub n, there's no fancy notation for it. So we have that, okay. Now, here's what we're going to do. We are going to inductively create our subsequence, and we're going to inductively create it so that the following holds. So x sub nk minus alpha is always less than 1 over k. And that guarantees that the subsequence that I have must actually converge to the lim sup, because given an epsilon, there is a 1 over n, where 1 over n gets less than epsilon and stays less than it. And there we go. Okay, so that's the plan of attack. That's all we're going to do. So we've got our lim sup, which is an infimum of a bunch of supremums, and we are going to show how to create this inductively. So we will demonstrate how to create the first term, and then we'll go, assuming we've created m terms, how do I make m plus 1? Okay. So, alpha is the greatest lower bound of the set of b sub n's, and again, we'll recall what the b sub n's are in a moment, but anyway, this is the greatest lower bound of this set, so that means that if I add 1, I can find something out of the set that is less than or equal to it. Right, this is the biggest lower bound, so this can't be a lower bound, so there's something from the set that lives here. Okay. Now what are the b sub n's again? The b sub n's are the supremums of the tails. So, this is the least upper bound of this set, so if I subtract 1 off of it, this can't be an upper bound, because this one over here is the least. So there's something from the set that lives between it. So note, I have an inf, so I added 1 to pick up an element. This is a sup, so I subtract 1 from it to pick up something out of my sequence. And then now I combine these two together, and I get alpha minus 1 is less than or equal to beta n minus 1. That's strictly less than alpha x sub n sub 1, which is less than or equal to b sub n plus 1, because remember, b sub n plus 1. No, that's just less than or equal. That's not supposed to be a plus 1. That's supposed to be a sub. That's a typo. I was like, what the hell, where was that going? No, right, because we've got this, which is, it's fixed on itself, hold on, which is less than this, right, because it's an element of the set, and that's an upper bound for it, and then that's less than the alpha plus 1. Alright, there we go. Sorry. Instead of sub, right, so when I typed it, I had shift, and then I did, instead of underscore, I misclicked and got the plus. I didn't notice. Ding dangle. Gosh darn diddly do. Alright, anyway, not too bad. Alright, there we go. So that combines it together, and then now you subtract the alpha over, and then we get the absolute value that's less than 1. Alright, so again, note what happened here. We had we have our alpha, which is what we're trying to work with. We used the fact of it that it is a infimum, so we added 1. So note, we're going to add something else next time. That picks up a b sub n, so we pushed our lower bound forward to grab an element. The element I grabbed is a least upper bound, so I pulled it back to pick up a element of the sequence, and then that has to live in between the push forward and the pull back. And there we go. Okay, so now we have these two inequalities, and we effectively invoked both of them to great effect. Okay, so this is essentially what we're going to do in the next phase of the proof. So here's the inductive base case. We verified that I can find something that's within 1 of alpha. Now, the basic idea is going to apply for the induction hypothesis, where we're going to suppose I've created a finite number of elements, and then I'll tell you how to make the next one. And we're basically going to do the same thing. Alpha is a greatest lower bound, so if I push it forward, I can pick up a least upper bound that I can then pull back and grab an element. The only thing we need to be mindful of is that I need to be creating a subsequence, which means I need my n sub 1s and n sub 2s and n sub 3s to be a strictly increasing sequence. And that's going to give us this technical nonsense we got to deal with, as I was mentioning. But the core idea of the proof of I'm taking a infimum, pushing it forward, that's grabbing the a supremum, which I then pull back to grab elements that I'm interested in. So it's a push forward, pull back kind of argument. And that kind of trick does happen quite a few times in analysis, but sparingly. This is kind of the first time we're going to see it. It'll pop up when we get to integration, which will be the last week or so of the course. Alright, so like I said, we are in an inductive argument, so let's suppose that we've created our subsequence. So I have my strictly increasing n sub 1 to n sub k, and they all have the desired property that I've got. The distance from these to alpha is 1 over j. Okay, now here's the tricky bit. Like I said, we need to guarantee a strict increase. So now we're actually going to use the fact that the limit of the sequence of b sub n's, which again, remember, these are the supremums of the tails, this actually converges. So that means there is a capital N, so that the distance that from b sub n to alpha is less than 1 over k plus 1. And note that this would then guarantee that b sub n minus alpha is strictly less than this, so we can add the alpha over. And it turns out this is what we really are going to need. Alright, so now what? Alright, so now we will set m to be the maximum of n, and the maximum of n sub k plus 1. Note that's something strictly bigger than this. And again, we need to create a subsequence, so I need the strict increasing. Okay. Now, n is less than m, because m is the maximum of n in this thing. And this is monotone decreasing, remember. So that means b sub n is less than or equal to b sub n, and b sub n we chose so we had less than this. B sub m is a least upper bound of something. So if I pull off a term, I can find a x sub j. Note, the j needs to be at least m. M is bigger than this, which is strictly less than n sub k, and there we go. And then my x sub j then it needs to be bigger than this, but less than or equal to that. So here, right, note we sort of did the push the infimum forward and pick an element, but we needed to actually use the convergence to get the 1 over k plus 1. And this was needed because we need the monotone decreasing part of it. You couldn't just do the, oh, if you add 1 over k, you pick something up. You need to be further out enough to make it work here. Alright. So we got that, and then, so there was our push forward to get what we needed, and here's our pullback to get what we need as well. Okay, so here we see that same sort of argument, the push forward and then the pullback, but note there's some technical junk going around this time, whereas before there wasn't. But the same idea of, I'm taking my inf and pushing it forward, and that gives me a soup that I then pull back to grab an element. Alright, so, to finish things off, the j that we guaranteed to exist is strictly bigger than n sub k, so we'll make that our n sub k plus 1. Note that that's true. And as alpha is a lower bound for all of these soups, that means b sub m is bigger than it. B sub m minus k plus 1, strictly less than x sub j, and x sub j is less than or equal to b sub m, which we know is strictly less than alpha plus 1 over k plus 1. So subtract the alpha across, and we get the inequality we seek, and thus we have created our subsequence as desired. Whew. There you go. So, like I said, this is probably going to be the worst theorem we're going to prove in terms of just how much junk is flying around. And again, the core idea isn't too awful. I have a infimum of supremums, so push it forward, and then pull these back. So the core idea isn't too crazy. But there's a lot of detail. A lot of ins, a lot of outs, a lot of what have yous. And that's what makes this really the first result we've had in this course. It's kind of brutal. But like I said, it's not awful, right? But it's probably going to be the worst one. And not because it's the most difficult one, just because it's the first every math textbook. So here's a side note. Every math textbook always kind of hits a point where they go like, okay, we're going to prove now the first non-trivial thing. Like every math textbook has that moment where the author kind of goes like, all right, we're done screwing around, and I guess this is ours. This is our first real meaty theorem, I guess. So kind of very famously in measure theory, pretty much every measure theory book, which is about integration, basically says up until you get to Lebesgue's monotone theorem, everything before that's trivial. Lebesgue's monotone theorem is that's when you actually prove something legit. And it is kind of true. Topology is another branch that has a similar theorem. Something called Urey-Jones lemma is the first thing where they're like, okay, this is the real shit now. This is the actual... And that one really has a pretty good claim for that, because Urey-Jones lemma is one of those... To this day, I think is still one of the most it's shocking why that's even true. Even seeing the proof and knowing the proof, it's just wow, how is that even kind of deal? Anyway, all right. Well, we've proven the Bolzano-Weierstrass theorem. We now know that every bounded sequence has convergent subsequences. Specifically, every bounded sequence has subsequences that converge to the limit inferior and the limit superior. And I mentioned something similar to this, and while I'm rambling here, a favorite phrase of mine is, if the math gods let us prove something, it's because they want us to use it. And I got that quote from a mathematician named Joe Dietzel, who is no longer with us, unfortunately. He was a professor at Kent State, and he was the organizer of the Kent State Analysis Seminar, which is a pretty legendary analysis seminar. He was telling, I actually met him a couple of times, and he was telling me about, like, the very first one was, like, a complete nightmare. It was during a blizzard, like, nobody showed up for it. And anyway, so he's got a pretty interesting. He wrote a book, and he basically opens the book with the quote of, "Right, If you're able to prove something, it's because the math gods want you to use it." So we've proven the Bolzano-Weierstrass theorem. The math gods want us to use it, so let's use it. Okay. So, first up on our applications of our very wonderful theorem, let's say you've got a bounded sequence. If my sequence is convergent, then the lim sup and the lim inf have to equal the limit. And conversely, if I have a bounded sequence and the lim sup and the lim inf are equal, then my sequence must converge. This actually gives us a way of detecting convergent and divergent series sequences. If I have a sequence whose lim inf and lim sup are not equal to each other, it has to diverge. Very cool. Very neat. Okay. Alright, so first up. So if our sequence does converge, that means we know every subsequence converges to the original limit. And by Bolzano-Weierstrass, that means the lim sup and the lim inf have to converge to the limit of the sequence, right? Because I have subsequences that converge, and if we are a convergent sequence, every subsequence must converge. Alright. Now, let's demonstrate that if I know the lim inf and the lim sup are equal, then my sequence must be convergent, and specifically it converges to whatever the lim sup was. And then, vicariously, the lim inf. Alright, so again, we'll set up our a sub n's and b sub n's. A sub n is the infimum of the tails, b sub n is the supremum of the tails. Note, for any n, this is true. In fact, we pointed this out. Oh, hey, this sequence converges, and they're the same. They're limits. By sandwich theorem, we're done. Proof's over. Beautiful. Really cool. Right. So remember, the lim sup is the... Oh, I got it. Ooh, blip. Got it backwards. It's lim inf. Ugh. Oof. Typo. Typo negative. Right there. On fire with the esoteric references today. You know what happened there? I copied and pasted from here. Bit me in the ass on that one. Alright. Anyway. Alright, beautiful. There you go. And, yeah! There we go. So, here we have a way of detecting convergence by using the lim inf and the lim sup. Good stuff. Okay, so we got a couple more to finish the story, at least for now. Alright, so what we're going to prove now is that if I have a bounded sequence, and I look at a subsequence, so note the subsequence itself must be bounded, because it's just terms of the sequence, but fewer, potentially. So it's still bounded. And thus we've got access to lim inf and lim sup of those, and the lim inf and the lim sup of a subsequence behaves the way you expect it to. Meaning that if I take terms away, which is what I do in a subsequence, the infimum could only get bigger. I can't get smaller. I took things away. So whatever my original bounds were, they remain where they were. And likewise with the sup. Alright, so specifically we'll prove the second equality, and then note the first one is proven similarly. Alright, so let's set up what we're going to compare. Okay, so b sub n will be the sups of the tails of the original sequence, and c sub n will be the sups of the tails of the subsequences. Now remember, with subsequences, we've got the strict increasing property, so k is always less than or equal to n sub k. So if I have an n sub k where k is bigger than n, Well, n sub k then is bigger than n, so n sub k must hang out in the set over here. So I have subset in this direction, and as we discussed last time, that guarantees that the soup over here is less than or equal to the soup over there. Right, because note, any upper bound here would be an upper bound for this set. So b sub n is an upper bound for this. Anything that's in here is an upper bound for b sub n. C sub n is the soup, so it's the least upper bound of the set. So since b sub n is an upper bound for this, that means it's less than or equal to the soup of that set, giving me the inequality. Alright, and hey, this is good for all n, and now we didn't explicitly prove this fact, but we know that the limits of these sequences exist, which means that the limits have to behave like this. We proved the sandwich theorem instead. The proof of that can be modified to verify that if I've got this less than that, then this limit works the way I want, and thus that gives me the lim soups inequality that I desired as well. Beautiful. Alright, let's finish this. So one last fact, and this is a very illuminating fact. So the last illuminating piece of information about subsequences and their relation to lim-inf and lim-sup. If I have a bounded sequence and a convergent subsequence, then the limit of that convergent subsequence lives between the lim-inf and the lim-sup. Now note, what does that mean? Another reading of this, lim-inf, remember, is the limit of a subsequence. And so is lim-sup. And this says that for any subsequence that converges, whatever it converges to cannot be less than the limit inferior, and it cannot exceed the limit superior. So in other words, lim-sup and lim-inf are the largest and smallest subsequential limits. So any subsequence that converges, their outputs have to live. Wherever that converges, it has to be between the lim-inf and the lim-sup, no matter what. It's a really interesting result. In fact, this is another way of characterizing. So this actually reveals another avenue we could have taken when creating lim-inf and lim-sup. What we could have done is defined the subset of subsequential limits, so the collection of things that are limits of subsequences, and then prove that there is in fact the largest and the smallest thing that they have to converge to, and then just call those the lim-inf and the lim-sup, and then verify that they have the properties we so desire. Alright, let's finish this, and this one just follows from the previous fact. Lim-inf of a sequence is always less than or equal to lim-inf of the subsequence. If I have a convergent sequence, its limit must equal its lim-inf, and its limit must equal its lim-sup. But lim-sup here goes bigger than that, and there we go. Beautiful. Alright. And that wraps up our little story on subsequences, and proving some very essential and important facts. Alright. Okay, so, one more video after this, and I've already mentioned his name, but we're going to go hang out with ya boy Koshi, so I'll see you then for that video.